Right now, tonight, there are more than 15,000 satellites quietly circling above your head. 2/3 of them belong to one company, and in a filing most people will never read, that same company has asked permission to launch nearly 1 million more. Not for internet, not for phone calls, to run artificial intelligence. Here's what should genuinely unsettle you. Every one of those machines is moving at roughly 27,000 kilometers an hour, close enough to its neighbors that a single collision could shatter into thousands of fragments, and each fragment becomes its own bullet, hunting for the next satellite in line. Physicists have a name for what happens after that. They call it a cascade, and once it starts, there may be no way to stop it. We could wake up one morning to a sky sealed shut, a species quietly, permanently grounded on its own planet. Tonight, we're going to walk through exactly how that happens, step by step, law by law, launch by launch. Get comfortable. Hit subscribe if this is your first time here, because by the end of tonight, you'll understand exactly how close we already are to the ceiling closing over our heads. Now let's slowly ease into this. Part 1. The Man Who Saw It Coming. In 1978, a NASA scientist named Donald Kessler sat down and did something almost nobody else in the space industry was doing at the time. He did the math on garbage, not on rockets, not on payloads, not on the glossy future of satellites beaming data down from orbit. Kessler looked instead at what happens to all the debris left behind once a spacecraft finishes its job, the spent rocket stages, the flecks of paint, the tiny bolts that shake loose during launch. And he asked a simple question. What happens if we just keep adding more of it, year after year, without ever really cleaning up? The answer he arrived at was so unsettling that it eventually took his name. The Kessler Syndrome. And the core of it is almost embarrassingly simple to state, even though the physics underneath it is anything but simple. Every object in low Earth orbit is moving at somewhere around 28,000 kilometers an hour. At that speed, if two objects collide, they don't crumple like cars in a parking lot. They vaporize into a cloud of fragments, and each fragment inherits enough of that original velocity to become a projectile in its own right. A screw, a washer, a shard of solar panel, all of it now moving fast enough to punch straight through the hull of another spacecraft. And here is the part of Kessler's insight that made his colleagues uncomfortable. Once the density of objects in a given orbital shell crosses a certain threshold, collisions don't need a cause anymore. They become statistically inevitable. You don't need two satellites to be aimed at each other. You just need enough clutter up there that, sooner or later, two paths cross. And when they do, the collision doesn't reduce the amount of debris in orbit, it multiplies it. One dead satellite becomes 1,000 shards. Each of those shards can go on to strike something else, creating thousands more. It is, in the truest sense of the phrase, a chain reaction. Not fire, not radioactivity, just velocity, endlessly propagating itself through the empty dark above your house. When Kessler first published this, low Earth orbit held a few thousand tracked objects. It was a genuine scientific curiosity, the kind of paper that gets cited respectfully and then mostly left in a drawer, because in the 1970s and 80s and 90s, there simply wasn't enough up there for the cascade to matter. Nobody was launching at a pace that could trigger it. The sky felt, for all practical purposes, infinite. That assumption held for almost 40 years. And then it quietly, decisively broke. I want you to sit with a number for a moment, because I think it's easy to hear a statistic like this and let it slide past you without actually feeling its size. in the entire history of spaceflight, starting with Sputnik in 1957 and running all the way through every rocket, every space station module, every satellite ever put into orbit by every country on Earth. Humanity has launched something in the neighborhood of 20,000 tons of material into space. That's the entire tally. 7 decades of rockets. And it comes out to 20,000 tons. Now hold that number next to this one. A single company has filed paperwork proposing satellites that, if built as described, would weigh close to 2 million tons once the full constellation is in orbit. Not 20,000. 2 million. 100 times more mass than every human being has ever managed to lift off this planet, combined in the entire span of the space age. And that same company is not the only one filing. Others are lining up behind it, each with their own plans, each wanting their own slice of the same orbital shells. This is the moment where Kessler's 40-year-old warning stops being a thought experiment and starts becoming an engineering constraint that the entire species has to reckon with, whether it wants to or not. Because here's the thing about orbital shells that most people never think about. Space feels infinite when you look up at it. It isn't. Low Earth orbit is not some boundless ocean where you can just keep adding boats forever. It is a finite, structured region sliced into specific altitude bands that satellites tend to cluster in. Because those altitudes are the ones that make the most engineering sense, close enough to Earth for low latency communication, high enough to avoid the drag of the upper atmosphere. And when tens of thousands of new objects get crammed into the same narrow bands, the space between them stops being generous. It starts being close. Dangerously close. Right now, today, operators are already dodging constantly. The current constellations in orbit are performing what are called collision avoidance maneuvers thousands of times a month. Small automated nudges where a satellite's onboard computer looks at incoming trajectory data, calculates that another object is going to pass uncomfortably near, and quietly fires a thruster to slide out of the way. Most of the time, you never hear about it. It happens silently, automatically, an invisible traffic control system keeping the whole fragile arrangement from tearing itself apart. But automated avoidance only works under a specific set of assumptions. It assumes the satellites can still steer. It assumes the tracking data is accurate and current. It assumes there's enough time between detecting a threat and reacting to it. And most of all, it assumes there aren't so many objects up there that the sheer number of potential near misses overwhelms the system's ability to respond to all of them. Every one of those assumptions gets shakier as the population in orbit grows. And that population isn't growing by a few % a year anymore. It's growing by orders of magnitude. Because the thing being launched into orbit today isn't just a communications relay anymore. It's something far hungrier, far heavier, and far more permanent than anything Donald Kessler could have imagined sitting at his desk in 1978. Because the newest satellites being proposed aren't going up to bounce a phone signal around the planet. They're going up to think. Somewhere on Earth tonight, in a windowless building humming with the sound of 10,000 fans, a machine is drawing more electricity than an entire neighborhood just to answer a handful of questions typed into a chat window. And the people who built that machine have looked at the size of the problem, looked at the limits of the power grid holding them back, and come to a genuinely audacious conclusion. If there isn't enough room, and there isn't enough power down here on the ground, then maybe the solution isn't to build smaller. Maybe the solution is to leave the ground behind entirely. That is where our story actually begins. Not with rockets, and not with satellites, but with a hunger for electricity so enormous, that an entire industry has started looking up at the sky and asking a question that would have sounded insane a decade ago. What if we just moved the data centers into orbit? To understand why that question is even being asked seriously, we need to go back down to Earth first, to a single building outside Memphis, Tennessee, where the true scale of what artificial intelligence actually costs became impossible to ignore. Part 2. The hunger that started it all. Picture a warehouse the length of several football fields, windowless, humming, lit only by the cold blue glow of status lights blinking across rack after rack of machines. Inside, there is no one. Almost no one. A handful of engineers walk the aisles with laptops, checking temperatures, listening for the specific pitch of a fan that's about to fail. Everything else is automated, and the electricity flowing into this one building every single day would be enough to light up a small city. This is what a modern AI data center looks like from the inside. And in the last few years, dozens of them have gone up across the world, each one bigger, hungrier, and faster to build than the last. Some of the newest facilities were constructed in under 4 months, a pace that would have been unthinkable for industrial infrastructure a decade ago. Steel goes up, chips go in, and within weeks the building is drawing power measured not in the units your house uses, but in the units a small nation uses. Here is the number that ought to stop you. In 2024 alone, data centers built specifically to train and run artificial intelligence consumed something in the neighborhood of 400 terawatt hours of electricity worldwide. To put that in a shape your mind can actually hold, that is more electricity than the entire United Kingdom, 67 million people, used in the same 12 months. One category of building, on one narrow industry, outdrawing an entire developed nation. And it is not slowing down. Every serious industry projection has that number more than doubling before the end of the decade. Every time you type a question into an AI chatbot somewhere, a rack of processors lights up and pulls electricity out of a grid that was never designed to carry this kind of load. The problem is not that we don't know how to generate more electricity. We do. The problem is timing. A data center, once you have the money and the chips, can be built in about a year. A new power plant, depending on the type, takes anywhere from 3 to 7 years to plan, permit, and construct. And the transmission lines needed to actually carry that new power from the plant to the data center, the literal cables strung across the countryside, can take the better part of a decade to approve and build, snarled in permitting, land rights, and local opposition. So you end up with a strange, almost absurd mismatch. Companies that can build a building full of chips in 12 months, sitting there, finished, ready, waiting years for the grid to catch up to them. In some regions, this mismatch has already tipped into outright crisis. Grid operators in parts of Europe have had to freeze new data center connections entirely, a flat moratorium, because they were genuinely afraid that adding one more facility would push the local grid into rolling blackouts. Not a hypothetical fear, an engineering judgment made by the people whose job it is to keep the lights on for everyone else. And electricity is only half of the problem. The other half is heat. Every calculation an AI chip performs generates waste heat. And modern AI processors run so densely packed, so many transistors switching so many times per second, that keeping them from literally melting has become one of the defining engineering challenges of the entire industry. The cheapest, most effective way to pull that heat away is water. Enormous quantities of it, pumped through cooling systems, evaporated into the air day after day. A single large data center can consume millions of gallons of water daily, water that in many regions is already stretched thin by drought agriculture, and the needs of the people who live nearby. So here is where the industry found itself, boxed in on one side by a power grid that cannot expand fast enough, and boxed in on the other by a planet that cannot supply endless water to cool machines that are only getting hungrier. And it was somewhere in the middle of grappling with that exact bind that a strange, almost radical idea started circulating seriously in boardrooms that a decade earlier would have been laughed out of the room. What if you didn't need the grid at all? What if you went somewhere the sun never sets, where there is no permitting process, no neighbours to file noise complaints, no water table to worry about, and no clouds to ever block your solar panels? What if, instead of fighting for scraps of electricity down here, you simply took the computers up there? In low Earth orbit, a solar panel doesn't experience day and night the way we do. Depending on the altitude and the specific orbit chosen, a satellite can spend the overwhelming majority of its time in direct, unfiltered, unobstructed sunlight that hasn't been dimmed by passing through 60 miles of atmosphere, hasn't been scattered by clouds, hasn't been interrupted by a rainy week or a long winter. It is, from a pure energy perspective, close to the most efficient solar collection environment physically available to us anywhere in the solar system, short of flying directly at the sun itself. And when engineers looked at that fact next to the crushing energy demands of AI computation, an idea that had circulated on the fringes of aerospace thinking for decades, orbital solar power, suddenly found itself with an entirely new reason to exist. Not to beam power back down to Earth, which had always been the old dream and always ran into the brutal difficulty of transmitting energy across hundreds of kilometers of empty space efficiently. Instead, the new idea skipped the transmission problem entirely. Don't send the power down, send the computer up. Let the whole data center exist in orbit, drawing its electricity directly from unfiltered sunlight, needing no cables, no grid connection, no local utility company at all. It is, on paper, an almost elegant solution to a problem that had felt intractable on the ground. And in the earliest months of this year, one of the largest aerospace companies on the planet made that idea concrete. Not a thought experiment in a research paper. An actual regulatory filing submitted to the body that governs American satellite launches, proposing a constellation of AI-powered satellites so vast that the number attached to it initially seemed like a typo. Up to 1 million individual spacecraft, each one a self-contained data center, floating in interconnected shells above the Earth, running on sunlight, cooled by nothing but the void itself, and talking to each other across the emptiness with beams of laser light. The company framed the proposal in genuinely grand terms, describing it as an early step toward humanity harnessing the kind of energy scale that, on a famous scale used by astronomers to categorize the power output of entire civilizations, would put us meaningfully further along the path from a species confined to one planet towards something that commands the energy of its entire star. Ambitious language. The kind of language that sounds inspiring in a keynote and unsettling in a legal filing. Because the moment you actually try to picture what 1 million satellites in orbit looks like, the elegance of the idea starts to run headlong into a set of physical realities that nobody standing on a stage tends to dwell on for very long. The heat those satellites would need to shed, the radiation that would slowly kill their chips, the sheer staggering mass that would need to be launched over and over again forever just to keep the constellation alive, and most unsettling of all, the traffic. Because space, it turns out, is not the boundless, empty freedom that the marketing language wants you to imagine. It has lanes, it has intersections, and the more objects you put into those lanes, moving at speeds fast enough to turn a fleck of paint into a bullet, the closer you inch toward the exact scenario Donald Kessler warned about, sitting at his desk, decades before anyone had thought to ask a computer to write an email. To understand just how real that danger is, we first need to understand something almost nobody outside the aerospace industry ever thinks about. Space is not cold in the way you assume it is. And that single misunderstanding is about to become one of the most expensive engineering problems humanity has ever tried to solve. Part 3. The cold that isn't cold. Here is an assumption almost everyone makes the first time they hear about computers in space, and it is wrong in a way that turns out to matter enormously. Space is cold. Famously, brutally cold. Out beyond the last wisps of atmosphere, the temperature can plunge to somewhere near minus 270 degrees Celsius, just a few degrees above the coldest anything can theoretically get. Surely the thinking goes, if you park a computer out there, it will simply sit in that endless cold and stay comfortably chilled forever. No fans required, no cooling towers, no water bill. It sounds intuitive. It is almost completely backwards. To understand why, you have to think carefully about what temperature actually means and how heat actually moves. Down here on Earth, when something gets hot, it has 3 ways to shed that heat. It can conduct, passing warmth directly into whatever it's touching, the way a hot pan cools down against a marble countertop. It can convect, releasing heat into moving air or moving water, the way a fan cools your laptop or a river cools a power plant. Or it can radiate, glowing faintly in infrared light, the way your own body does right now, invisible to your eyes but perfectly visible to a thermal camera. Conduction and convection both depend on one thing. They need matter. They need something physically touching the hot object, air molecules, water molecules, metal atoms, something to physically carry the energy away. In the vacuum of space, there is no matter to carry anything away, no air to blow across a hot surface, no water to pump through a radiator and cool in the breeze, no countertop for a hot object to rest against. There is, for all practical purposes, nothing, and that means a satellite in orbit only has one single option left for getting rid of the heat its electronics generate. It has to glow. It has to radiate that heat away as infrared light, the exact same slow, quiet mechanism your own skin uses to cool itself in a dark room, except a satellite doesn't have the luxury of sweat or a breeze or a cold glass of water. It only has the glow. And here's the part that catches almost everyone off guard. Glowing is a spectacularly inefficient way to move heat compared to conduction or convection. It works, but it works slowly, and the amount of heat you can shed this way depends entirely on how much surface area you can expose to the emptiness around you, and how hot you're willing to let that surface get. This is why the International Space Station, despite floating in a supposedly freezing environment, needs those enormous white wing-like panels you always see in photographs, panels that have nothing to do with solar power and everything to do with cooling. The station generates something in the neighborhood of 70 kilowatts of waste heat from its life support systems, its lighting, its instruments, its computers. And to get rid of that modest amount of heat, engineers had to build over 150 square meters of dedicated radiator panels, structures weighing several tons, purpose-built to glow that heat away into the dark. 70 kilowatts. That's less waste heat than a single high-end AI server rack generates down here on the ground today. Now hold that thought next to the actual specifications described in this year's proposals for orbital AI satellites. A single one of these spacecraft, is described as carrying well over 100 kilowatts of active computing power, which means well over 100 kilowatts of waste heat that has to be radiated away using nothing but the glow in an environment where there is no air, no water, and no shortcut. If you look at the design sketches for these satellites, your eye is naturally drawn to the two enormous panels stretching out on either side, and your first instinct is to assume those must be the radiators, the cooling system, doing the heavy lifting. They aren't. Those huge wing-like structures are almost entirely solar panels, hundreds of square meters of them, there to soak up sunlight and generate electricity. The actual cooling system is a comparatively thin strip running down the center of the spacecraft, a fraction of the surface area, tasked with shedding all of that waste heat into the void. At first glance, the math doesn't seem to work. If you run a radiator panel at a comfortable temperature, something close to room temperature here on Earth, the physics of thermal radiation says it can only shed a modest few hundred watts per square meter. Multiply that by the available radiator area on one of these satellites, and you land well short of the total heat that needs to go somewhere. At room temperature, the numbers simply don't close, which forces engineers into a choice that sounds almost reckless. Let it run hot. Genuinely hot, tens of degrees above what would ever be comfortable inside a data center on the ground. Here's why that choice actually works, and it comes down to one of the more beautiful and unforgiving relationships in physics. The amount of heat a surface radiates away doesn't increase in a straight line as it gets hotter. It increases with the fourth power of its temperature, which means a relatively modest increase in operating temperature produces a dramatic increase in how much heat a radiator can shed. Warm that thin center strip up to somewhere in the high 40s Celsius, and it can plausibly handle the full heat load of the spacecraft's normal operations. Push it hotter still into the low 60s, and it can cope with the heat spikes generated during the most demanding computational bursts. Modern silicon chips can genuinely tolerate temperatures like that. It's uncomfortable by the standards of a climate-controlled server room, but it is not destructive. And so the entire design philosophy behind these orbital data centers rests on a strategy that would sound almost absurd if you said it plainly. Deliberately overheat the computer on purpose, because running hot is the only way to make the physics of radiating heat into a vacuum actually balance the books. It's an elegant workaround, and to be clear, it isn't pure speculation. Small-scale experiments have already proven pieces of this concept work in the real world. A startup has already flown a genuine, commercially available AI processor into orbit and successfully run a small model on it, glowing its waste heat away exactly the way the physics predicts. Other countries have already begun linking small clusters of AI-capable satellites together using laser communication, testing exactly the kind of interconnected orbital network that a full-scale constellation would eventually require. So the thermal engineering, difficult as it sounds, is not the thing standing in the way. There is no law of physics that forbids a satellite from running as an overheated, glowing, functioning data center in orbit. Given the right materials, the right chip design, and the right radiator geometry, it works. But surviving the heat is only the first hurdle. The second hurdle is surviving everything else that space throws at exposed electronics, hour after hour, for years on end, without a single technician ever able to walk up and swap out a failing part. And the third hurdle, the one that ultimately governs whether any of this ever actually happens at the scale being proposed, is the coldest, most unglamorous constraint of all: money. Because it turns out that even if you solve the heat problem perfectly, there is a brutal economic wall standing between today's launch costs and the price this entire vision needs to hit in order to make any financial sense at all. That's where we're headed next, into the radiation that quietly kills these satellites years before their time, and the staggering math of what it would actually cost to keep replacing them, forever, just to stand still. Part 4. The Invisible Executioner. There is a particular kind of violence that happens in orbit that has nothing to do with collisions, nothing to do with debris, and everything to do with something you cannot see, cannot hear, and cannot shield against completely. Radiation, not the dramatic, glowing, science fiction kind. The quiet, relentless, particle by particle kind, streaming constantly from the sun and from deep space, passing straight through the thin, aluminum skin of a satellite as though it weren't even there. Down here on Earth, you are protected from almost all of this by two enormous, invisible shields working together. The planet's magnetic field, generated by the churning molten iron thousands of kilometers beneath your feet, deflects the overwhelming majority of charged particles streaming outward from the sun, bending their paths around the planet like a river splitting around a boulder. And the atmosphere itself, that thin blue layer of air you never think twice about, absorbs most of what does get through, scattering high-energy particles into showers of lower-energy ones long before they ever reach the ground. A satellite in low Earth orbit still benefits from some of that magnetic protection, but nowhere near as much as you might hope, and the higher the orbit climbs, the thinner that protection becomes. Above certain altitudes, spacecraft pass directly through regions of concentrated charged particles trapped by the Earth's own magnetic field, donut-shaped belts of radiation first mapped in the earliest days of the space age, regions so intense that engineers deliberately route sensitive spacecraft around them whenever possible. And even outside those belts, satellites are still bathed continuously in a background hum of cosmic rays, high-energy particles that have been travelling since before our solar system existed, remnants of supernovae and other violent events scattered across the galaxy, now slamming randomly into anything solid enough to stop them. For a human being, this background radiation is a slow, cumulative health concern. One of the genuine hazards astronauts have to carefully manage on long missions. For a computer chip, it is something far more immediate and far more destructive. Modern processors pack billions of transistors into an area smaller than a postage stamp, each one a microscopic switch representing a single bit of information, a 1 or a 0. When a sufficiently energetic particle strikes one of those transistors, it can deposit enough charge to flip that switch, silently, instantly, corrupting whatever calculation was happening at that exact moment. Engineers call this a single event upset, and in the world of computing it is exactly what it sounds like. A tiny, invisible act of sabotage, committed by a particle that has been travelling through the emptiness of space for millions of years before it happened to intersect with your satellite at the precise wrong moment. Most of the time, a single flipped bit is a minor annoyance, an error that gets caught and corrected by redundant systems built specifically to catch this kind of thing. But radiation doesn't stop at flipping the occasional bit. Over months and years of continuous bombardment, it does something far more permanent. It physically damages the silicon itself, degrading the delicate structures inside each transistor, gradually eroding the chip's ability to function correctly at all. This is why the electronics industry has an entire specialized category of components known as radiation-hardened chips, deliberately built with older, simpler, more robust designs specifically because that simplicity makes them more resistant to this slow accumulation of damage. And here lies one of the deepest tensions running straight through the middle of the orbital data center concept. The chips that are best at resisting radiation are, almost by definition, years behind the cutting edge. The entire value proposition of an AI data center rests on packing in the newest, densest, most powerful processors available, the kind being manufactured on the absolute frontier of chip fabrication technology. But those same cutting-edge processors, with their impossibly small transistors and razor-thin insulating layers, tend to be dramatically more vulnerable to radiation damage than their older, chunkier, radiation-hardened cousins. You can shield electronics to some degree, wrapping them in extra layers of metal to absorb incoming particles before they reach the sensitive silicon. But shielding adds mass, and mass is the one resource this entire industry is most desperate to minimize, because every extra kilogram has to be launched, and launching things is expensive in a way that shapes every single decision made in this field. So the honest, uncomfortable engineering reality is this. If you want your orbital data center to run the newest, most powerful AI chips available, the ones actually capable of doing meaningful work, you have to accept that radiation is going to steadily degrade them, and within roughly 5 years, by most current estimates, the damage accumulates to the point where the satellite's computing hardware simply isn't reliable enough to keep using. 5 years. Think about what that actually means at the scale being proposed. If a company genuinely intends to operate something approaching 1 million of these satellites, and each one has an effective computational lifespan of roughly 5 years before radiation degradation forces retirement, then the constellation isn't something you build once and walk away from. It becomes something you have to continuously, permanently rebuild. Every single year, a meaningful fraction of the entire fleet needs to be replaced, deorbited, and launched again from scratch, forever, for as long as the constellation is intended to keep operating. Multiply that fraction across the full proposed scale, and you arrive at a launch cadence that sounds almost impossible to sustain. Thousands of heavy rocket launches every single year, not as a temporary burst of construction, but as an ongoing, permanent operational requirement. Multiple launches a day, every day, indefinitely, just to replace hardware that radiation has quietly worn out. Not building towards some finished, stable endpoint. Running forever, just to stand still. Which brings us to the third hurdle, the one that ultimately determines whether any of this ever moves from ambitious filing to operational reality. Money. Every kilogram launched into orbit today costs real, substantial money, and that cost has been the single most important variable shaping the entire history of spaceflight. For decades, launching anything into orbit was so expensive that only governments, and occasionally the largest telecommunications companies, could seriously consider it. The last several years have seen that cost fall dramatically, thanks largely to reusable rocket technology. But even at today's improved prices, getting a single kilogram of hardware into low Earth orbit still costs somewhere in the range of $2,000 or more on the most cost-effective rockets currently flying. Independent analyses looking specifically at the economics of orbital data centers have arrived at a genuinely sobering conclusion. For space-based computing to become cost-competitive with building the equivalent capacity in a data center here on the ground, the price of launching a kilogram of hardware into orbit needs to fall to somewhere around $200. Not a modest improvement. A reduction of roughly 13 times from where costs sit today. That is an enormous gap to close, and the entire feasibility of the vision hinges on a single piece of hardware that as of this moment has never once successfully reached orbit. A massive, fully reusable rocket, still in active flight testing, still working through the inevitable failures and setbacks that come with developing genuinely new aerospace technology. If that rocket eventually performs the way its designers hope, launch costs could plausibly fall below the threshold needed to make orbital data centers economically viable. If it doesn't, or if it takes years longer than currently projected, the entire proposal remains exactly what it is today. An ambitious filing, sitting in a regulatory queue waiting on a piece of hardware that hasn't yet proven it can do the one thing everything else depends on. But here's the thing about ambitious filings in this industry. History has shown, again and again, that betting against these companies actually attempting what they file for tends to be the wrong bet. And even a partial version of this vision, a fraction of 1 million satellites rather than the full proposed constellation, would still represent an unprecedented addition of mass and traffic to an orbital environment that is already, right now, showing serious signs of strain. Which brings us to the part of this story that should genuinely concern you. Because even if every engineering problem gets solved, even if the heat gets managed and the radiation gets mitigated and the launch costs come tumbling down exactly as hoped, there remains one final constraint that no amount of clever engineering can simply design around. Space itself is not infinite. The orbital shells these satellites need to occupy are finite, structured, and increasingly crowded. And the closer that crowding gets to a critical threshold, the closer we edge toward the exact runaway scenario that Donald Kessler described sitting at his desk decades before anyone thought to ask whether we should fill the sky with computers. That's where we're headed next. Into the actual traffic patterns already unfolding in orbit today. The automated dodging that is quietly keeping disaster at bay right now, and the terrifying speed at which that safety margin has been shrinking. Part 5. The traffic nobody talks about. There is a kind of quiet miracle happening above your head every single day. One that almost nobody ever thinks about, and it is the only thing standing between the current state of orbit and outright catastrophe. It is called collision avoidance, and it has become, without most of the public ever realizing it, one of the largest ongoing automated safety operations in the history of engineering. Here is how it actually works. Every operational satellite in a major constellation is constantly fed a stream of tracking data, positions and predicted trajectories for every other tracked object sharing its orbital neighborhood, whether that object is a functioning spacecraft, a dead satellite, or a fragment of debris left over from some launch decades ago. Ground-based radar systems and optical telescopes around the world sweep the sky continuously, cataloguing the positions of tens of thousands of objects, feeding that data into software that calculates, for every satellite in the fleet, the probability that its path will bring it uncomfortably close to something else in the coming hours or days. When that probability crosses a certain threshold, the response is automatic. No human picks up a phone. No committee meets to discuss it. The satellite's onboard system simply fires its thrusters, nudges itself into a slightly different path, and continues on. Most of the time, this happens so smoothly and so routinely that the only evidence it occurred at all is a small entry in an operational log somewhere, unnoticed by everyone except the engineers whose job it is to keep the whole system running. The scale of this, right now, today, with only about 15,000 active satellites in orbit, is already almost impossible to casually grasp. In just the first 6 months of a recent year, One major satellite operator alone reported performing more than 140,000 of these automated avoidance maneuvers. Do the arithmetic on that number, and you land somewhere near 800 separate dodges every single day from one company's fleet alone. And across the full population of tracked objects sharing orbit right now, 2 objects pass close enough to trigger a genuine collision warning roughly once every 22 seconds. Read that again slowly. Once every 22 seconds, somewhere above the Earth, 2 objects moving at many kilometers per second come close enough to each other that the automated systems monitoring them flag it as a genuine risk requiring evasive action. And this is happening today with a fraction of the satellite population that has already been formally proposed for the coming decade. This is not a system with a comfortable margin of safety. This is a system running remarkably close to its operational limits, held together almost entirely by the fact that current satellites are capable of steering themselves out of harm's way, continuously, automatically, without fail, every single day. Which raises an obvious and deeply uncomfortable question. What happens if they suddenly couldn't? Space weather is not a metaphor. The sun periodically releases enormous bursts of charged particles and magnetic energy in events known as coronal mass ejections, and when a sufficiently powerful one strikes the Earth's magnetic field directly, it can wreak havoc on electronic systems far more sensitive than a simple radiation-induced bit flip. A truly severe solar storm has the potential to disrupt or temporarily disable the guidance and communication systems of satellites across an entire orbital shell simultaneously, not one satellite at a time, but potentially thousands at once, all losing their ability to reliably track their surroundings and maneuver out of danger in the exact same moment. Engineers and orbital safety researchers have actually modeled this scenario, asking a very specific and very unsettling question. If every satellite in a given shell simultaneously lost the ability to actively avoid collisions, how long would it take, on average, before something up there actually struck something else? The answer to that question, disturbingly, has been changing rapidly and not in the direction anyone would want. A few years ago, before the current generation of mega constellations had reached significant scale, researchers modelling this exact scenario estimated that the sky could go weeks, even months, without an active collision. Even in a worst-case scenario where every satellite lost its ability to maneuver simultaneously. Roughly 120 days of relative safety, even in the absolute worst case. 4 months of breathing room, enough time for engineers on the ground to diagnose the problem, restore control systems, and get satellites steering themselves again before disaster struck. As the population of active satellites climbed sharply in just the following years, that same modelling, rerun with updated numbers reflecting the current, far more crowded orbital environment, produced an answer that should genuinely alarm anyone paying attention. The estimated time before a collision became statistically likely in that same worst-case scenario had fallen to less than 3 days. Read that comparison again, because the speed of that change is the entire story. In roughly 7 years, the safety margin protecting us from a worst-case cascading collision scenario collapsed from about 4 months down to about 72 hours. Not because engineering standards got worse, and not because anyone became careless. Simply because the sheer number of objects sharing that orbital space climbed so quickly that the physics of probability caught up with us. More objects packed into the same finite volume means less room, less time, and less margin for error. Whether that error comes from a software glitch, a communications failure, or a solar storm severe enough to knock out steering systems across an entire constellation all at once. And there is one more variable in this equation that deserves careful attention, because it is the one factor that has quietly been protecting us, almost by accident, and it is a variable that the newest generation of proposed satellites is specifically designed to avoid. Altitude. Down at the lower altitudes where many current satellites operate, somewhere in the range of 500 to 600 kilometers above the surface, there remains a faint, almost immeasurably thin trace of the Earth's atmosphere. It is nowhere near enough to breathe, nowhere near enough to feel, but it is enough to create a very slight drag on anything moving through it at orbital speed. That drag acts like an extremely gentle, extremely patient brake. Over the course of just a few years, it is enough to pull a dead, uncontrolled satellite gradually downward, lower and lower, until it finally descends into the thicker atmosphere and burns up completely. This means that at these lower altitudes, orbit has a built-in, entirely natural self-cleaning mechanism. Debris created down there doesn't linger forever. It gets slowly, steadily swept away, typically within about 5 years, an automatic cosmic janitor working quietly in the background, removing exactly the kind of hazardous fragments that could otherwise accumulate indefinitely. But the newest proposed constellations are not confining themselves to these self-cleaning altitudes. The filings describe orbital shells stretching considerably higher, in some cases up to 2,000 kilometers above the surface. Altitudes chosen specifically because they offer more room to fit an enormous number of additional satellites without excessive crowding at any single altitude band, and because higher orbits mean more consistent, less interrupted exposure to sunlight, which matters enormously for a fleet of solar-powered data centers trying to maximize their computing uptime. At those higher altitudes, there is essentially no atmospheric drag left at all. The natural cleaning mechanism that quietly protects the lower orbital shells simply doesn't exist up there. A piece of debris created in a collision at 2,000 kilometers doesn't fall back to Earth and burn up within 5 convenient years. It can remain in orbit for centuries. In some cases, depending on the exact altitude and the specific characteristics of the debris, for thousands of years, circling silently, indefinitely, a permanent hazard added to an already crowded neighborhood, with no natural process capable of ever cleaning it up. Which means that the exact altitudes being chosen for this next wave of orbital data centers are, from a debris management perspective, precisely the wrong altitudes. Not because anyone is being careless, because those altitudes make the most engineering sense for maximizing sunlight and minimizing crowding at any single band. But the trade-off is stark. Choose an altitude that solves your power and spacing problems, and you choose an altitude where, if something ever does go wrong, the consequences don't fade away in 5 years, they become effectively permanent. And this is not a problem that belongs to any single company. Every nation, every private company with ambitions in orbit is going to end up competing for space within these same narrow finite altitude bands, all of them sharing the same limited volume, all of them dependent on the same fragile, automated dodging system to keep their satellites from tearing each other apart. Cooperation between all of these parties isn't a nice to have. It is the single thread everything else hangs from. Which brings us to the question that has been quietly building underneath everything we've covered so far. If a cascading collision scenario really did begin to unfold, what would it actually look like from where you're standing right now, looking up at the sky? And more importantly, once that door closes, is there any way to open it again? That's where we're headed next. Part 6. The night the sky goes silent. Let's actually walk through what a runaway cascade looks like, step by step, because it is one thing to hear the word Kessler Syndrome tossed around as a vague warning, and something else entirely to understand the specific mechanical sequence of events that turns a single accident into a permanent planet-wide problem. It starts small, almost disappointingly small. Two objects, somewhere in a crowded orbital shell, fail to avoid each other. Maybe a piece of tracking software makes a small error. Maybe a dead, uncontrollable satellite drifts into the path of an active one that has no way to know it's coming. Maybe, in the worst-case scenario, a solar storm has just knocked out these steering systems across an entire constellation simultaneously, and two spacecraft that would normally have dodged each other simply can't anymore. Whatever the trigger, the collision itself happens almost too fast to comprehend. Objects in these orbital shells are typically moving at somewhere around 7 or 8 kilometers per second relative to the Earth, and when two satellites on crossing paths meet, their combined closing speed can reach something in the neighborhood of 10 or 11 kilometers per second. To put that in terms your body can actually understand, that is roughly 30 times faster than a rifle bullet. At that speed, the collision doesn't look anything like two cars crumpling into each other. There is no slow-motion crunch of metal. The two spacecraft essentially vaporize each other on contact, converting almost all of their kinetic energy into an instantaneous expanding cloud of fragments, ranging from pieces the size of a car door down to flecks smaller than a grain of sand. This has actually happened, not as a thought experiment, but as a real, documented event. In February of 2009, an active American communications satellite and a defunct Russian military satellite collided directly over Siberia, the first time in the history of spaceflight that two intact satellites had ever struck each other in orbit. The collision generated well over 2,000 pieces of trackable debris large enough for ground-based radar to actually catalogue, and an unknown. Much larger number of smaller fragments too tiny to individually track, but still large enough at those speeds to destroy anything they happened to strike. That single event alone increased the total tracked debris population in low Earth orbit by a noticeable percentage overnight. One collision, two satellites, and the sky above the entire planet got measurably more dangerous within a matter of hours. And that wasn't even the worst deliberate demonstration of this danger. 2 years earlier, in January of 2007, a nation conducted a test of an anti-satellite weapon, deliberately destroying one of its own aging weather satellites with a missile, specifically to demonstrate the capability. That single test created more trackable debris than any other event in the history of spaceflight up to that point, scattering thousands of fragments across a wide range of altitudes, many of which remain in orbit to this day, nearly 2 decades later, still occasionally forcing other satellites, including the International Space Station itself, to perform emergency avoidance maneuvers to dodge fragments from a test conducted before some of the engineers currently tracking them were even born. These two events, one accidental, one deliberate, gave orbital debris researchers something they had never had before: real-world data. Actual proof of exactly how much debris a single collision generates. Exactly how far those fragments spread across different altitudes, and exactly how long they linger. And when researchers fed that real data into models simulating what happens if collision frequency increases beyond a certain threshold, the results confirmed something close to Kessler's original warning almost perfectly. Below a certain density of objects, individual collisions remain isolated, unfortunate events. Above that density, something fundamentally different happens. The debris from one collision increases the probability of a second collision. The debris from that second collision increases the probability of a third. And because each new collision doesn't just add debris arithmetically, it multiplies it, the process can accelerate rather than plateau, feeding on itself, growing consequences from a shrinking amount of remaining time. This is the runaway part of runaway cascade. It is not that one collision immediately fills the sky with an impenetrable wall of shrapnel. It's that a single event can raise the background collision risk across an entire shell high enough that further collisions become statistically inevitable, and each subsequent collision keeps raising that risk further, in a feedback loop that, once it passes a certain point, current technology has no real way to reverse. You cannot send a broom into orbit and sweep it clean. You cannot filter it out. The fragments are simply there, moving at bullet speeds, in numbers too vast and too widely scattered to practically remove, for as long as orbital mechanics and at higher altitudes the near total absence of atmospheric drag allow them to remain. Now project this forward into the world being proposed for the coming decade. Not 15,000 satellites, not 60,000, potentially well over 1 million spread across orbital shells that are already, today, generating a collision warning roughly once every 22 seconds among a vastly smaller population. Every additional satellite added to that environment doesn't just add one more object to track. It adds another point of failure, another possible trigger. Another opportunity for the automated avoidance systems that are currently holding everything together to encounter a scenario they weren't quite designed to handle in time. And here is the part of this that genuinely deserves to be called existential rather than merely inconvenient. If a cascade of this scale ever did begin in earnest, the consequences wouldn't be limited to the satellites themselves. They would extend to something far more fundamental: our ability to leave the planet at all. Every single crewed and uncrewed mission ever launched from Earth, every resupply flight to any future space station, every planetary probe, every telescope, every future mission to the Moon or to Mars, has to physically pass through low Earth orbit on its way out. It is not an optional waypoint. It is the unavoidable first few hundred kilometers of every single journey beyond our atmosphere. A rocket launching today accelerates up through the thick lower atmosphere, sheds its early stages, and then coasts through exactly the altitude range where these mega constellations are being deployed, before it can continue onward to anywhere else. If that altitude range became genuinely saturated with high-velocity debris, densely enough that the odds of a launching spacecraft surviving passage through it dropped to unacceptable levels, then for all practical purposes, humanity's physical access to space would be severed. Not through any deliberate decision. Not through any single dramatic event that makes headlines and then gets resolved. Through an accumulated self-reinforcing cloud of fragments that simply makes the mathematics of launching anything through it too dangerous to attempt, for years or decades, or at the highest altitudes where there is no atmospheric drag to eventually clean things up, for a span of time longer than most of human civilization has existed. This is not a scenario drawn from science fiction. It is the direct, logical, physically inevitable extension of trends that are already measurably underway, described using the exact same orbital mechanics that already govern the 15,000 satellites currently in the sky above you. The only genuinely uncertain variable is scale and timing, and whether the people currently filing paperwork to launch the next several 100,000 satellites are weighing this risk with the seriousness it actually deserves. Which brings us to an uncomfortable question that almost nobody outside a narrow circle of orbital safety researchers is currently asking loudly enough. Who, exactly, is supposed to be preventing this? Who has the authority to look at a proposal for 1 million new satellites, weigh the collision risk it introduces against the benefit it promises, and say no, or even simply not yet? The answer to that question turns out to be one of the strangest, most quietly alarming parts of this entire story, and it's where we're headed next. Part 7. The agency that was never built for this. Here is a question worth sitting with for a moment before I give you the answer, because the answer is genuinely stranger than most people expect. When a company files paperwork proposing to launch nearly 1 million new satellites into orbit, satellites that could reshape the visible night sky for every person on Earth and meaningfully increase the risk of a catastrophic, potentially permanent collision cascade, who actually reviews that proposal? Who has the authority to say yes, to say no, or to demand changes before granting permission? You might reasonably assume the answer involves some kind of international body. The United Nations, perhaps, or a dedicated global space agency, or at the very least some formal treaty process involving every nation with a stake in what happens above our shared atmosphere. Space, after all, belongs to no single country. The sky above your house tonight is the same sky above someone's house on the other side of the planet. The actual answer is almost none of that. In the United States, where the majority of the largest proposed constellations are being filed, the agency responsible for reviewing and approving these satellite launches is the Federal Communications Commission. An agency established in 1934, nearly a full quarter-century before the launch of the very first artificial satellite, for a purpose that had absolutely nothing to do with orbital debris, collision risk, or the visibility of stars in the night sky. It was created to prevent radio and television broadcasters from interfering with each other's signals here on Earth. That original narrow mandate still shapes almost everything the agency actually checks when a satellite proposal crosses its desk today. Because every satellite needs to communicate, sending and receiving data using specific slices of the radio spectrum, launching one requires securing the legal right to use that spectrum without stepping on the signals of everyone else already using it. And so when a company files paperwork for a constellation of any size, the primary technical question the reviewing agency actually evaluates is whether the proposed radio frequencies will interfere with existing users of that spectrum. That's it. That is, in large part, the actual substance of the review. Does the radio signal clash with someone else's radio signal? The agency does not have, as part of its formal statutory mandate, a requirement to evaluate how bright these satellites will appear in the night sky, or to weigh the cumulative impact of adding 1 million new reflective objects to an already crowded set of orbital shells, or to assess how a mass deorbiting event spread across thousands of satellites re-entering the atmosphere over the coming decades might affect the delicate chemistry of the upper atmosphere and the ozone layer that protects every living thing on the planet's surface. These are not questions the agency was built to ask, and in many cases, they are not questions the agency has clear legal authority to even require answers to. This isn't a hidden scandal buried in some obscure regulatory footnote. It's openly acknowledged by the researchers who study this field closely. One astronomer who has spent years modelling exactly how these mega constellations will change the appearance of the night sky put it about as plainly as it can be put. It is genuinely strange, she observed, that a single company, headquartered in one American state, seeking approval from one agency whose core expertise is radio interference, can make a decision that permanently alters the sky experienced by every single human being on Earth, in every country, regardless of whether that country had any say in the matter whatsoever. Think about the asymmetry embedded in that arrangement. A farmer in a remote village with no access to reliable internet, someone who has never once benefited from any satellite constellation, will still look up at their own night sky in 20 years and see it reshaped by a decision made in a regulatory filing they never knew existed. Reviewed by an agency in a country they may never visit, evaluating a question that had nothing to do with astronomy. Light pollution, or orbital safety. And it isn't only the visible sky that falls outside the scope of what typically gets reviewed. Orbital debris and collision risk assessments do exist, and regulatory frameworks in various countries have, over the past several years, begun requiring satellite operators to submit some form of debris mitigation plan alongside their launch applications. But the scale and rigor of these requirements vary enormously depending on which country's regulatory system a given company happens to be filing through, and there is no single, unified, binding global standard that every operator everywhere is required to meet before adding satellites to a shared orbital environment that recognizes no national borders. This creates what researchers in the field have started referring to with a kind of grim precision as a tragedy of the commons playing out at orbital altitude. Every individual company filing a proposal has a straightforward, rational incentive to launch as many satellites as it can, as quickly as it can, to establish itself in valuable orbital shells before competitors do the same. But low Earth orbit itself, the actual physical volume of space where these satellites need to operate, is a shared, finite resource. No single company owns it. No single country governs it. And the cumulative risk created by everyone rushing to fill it simultaneously isn't borne by any one filer. It's distributed across everyone who shares that orbital environment, and ultimately across everyone standing on the ground beneath it. There have been efforts to build something better. Various international scientific bodies, including organizations dedicated to protecting dark skies for astronomical research, have published detailed guidelines recommending specific limits, suggesting that the total satellite population in these lower shells should probably stay well under 100,000 if we want to preserve anything resembling a naturally dark, naturally visible night sky, and recommending that individual satellites be engineered to stay below certain brightness thresholds so they don't become the dominant, most visible objects in the sky wherever you happen to be standing. These guidelines carry real scientific weight. They are based on careful modelling, genuine expertise, and a sincere effort to find some kind of sustainable middle ground between the undeniable benefits these satellites provide, global internet access, scientific research capability, and now, potentially, distributed computing power, and the genuine costs they impose on astronomy, on the natural environment, and on the simple, ancient human experience of looking upward on a clear night and seeing stars rather than machines. But guidelines are exactly that. Guidelines. They carry no binding legal force. No company is required to follow them. No regulatory agency, in the United States or anywhere else, currently has clear authority to reject a proposal simply because it would push the total satellite population well beyond the thresholds these scientific bodies have recommended. And as things currently stand, the number of satellites already formally proposed across every filing from every major company and country, adding all of them together, comes to somewhere in the range of 1.5 to 2 million spacecraft, roughly 15 to 20 times higher than the upper limit that astronomers and dark sky researchers have suggested as the threshold for preserving a night sky that still resembles the one every previous generation of humans has ever known. We are not approaching that recommended limit cautiously from a comfortable distance, with time to reconsider. We have already, on paper, blown past it by an order of magnitude. and the agency with the actual legal authority to slow any of it down is one whose founding purpose has nothing to do with the sky at all. Which leaves us with the genuinely difficult question sitting underneath everything we've covered so far. If the regulatory guardrails are this thin and the collision risk is already climbing this fast, what does the actual future look like if every current trend simply continues on its present trajectory, unaltered, for the next 25 years? Not the optimistic version. Not the version in the promotional keynote. The version the physics and the filings actually point toward. Part 8. The sky your children will inherit. Let's walk forward together carefully, using nothing but the numbers we've already established, and see where they actually lead. Picture a clear, moonless night, 25 years from now, somewhere quiet, far enough from city lights that the sky should, in theory, be at its darkest and most revealing. You take someone younger than you outside, the way someone once took you outside, and you point upward, ready to show them something you remember vividly from your own childhood. The soft, hazy band of light stretching across the sky, our own galaxy, viewed edge on from the inside, a sight that required nothing more than a dark enough location and a patient set of eyes. Except now, that band is difficult to find. Not because it has vanished. The Milky Way hasn't gone anywhere, of course. It's precisely where it has always been, unimaginably far away, entirely indifferent to anything happening on this small planet orbiting one of its 100 billion stars. What's changed is what sits between you and it. Astronomers have already run detailed simulations projecting exactly what the night sky looks like as satellite populations climb toward the numbers currently sitting in regulatory filings, and the results are sobering in a very specific, quantifiable way. At a population of roughly 65,000 satellites, a number we are already most of the way toward reaching given everything currently approved or under active construction, researchers found that something in the neighborhood of 1 out of every 15 points of light visible in the night sky is no longer a star at all. It's a satellite catching and reflecting sunlight as it crosses silently overhead. Now scale that same modelling upward toward the full range of proposals currently filed across every major company and country combined, somewhere approaching 2 million spacecraft. Under perfectly dark skies, far from any city, the unaided human eye is capable of perceiving somewhere around 4,500 individual stars at any given moment. If even a substantial fraction of the proposed satellite population were actually deployed, the number of moving artificial points of light crossing that same field of view at any given moment could rival or exceed that number entirely. For much of the night, across much of the year, from nearly anywhere on the planet's surface, there would be more machines visible overhead than there are stars. And here's the detail that makes this genuinely different from every previous form of light pollution humanity has ever grappled with. Historically, if the sky above your home became too bright, too polluted, too obscured by artificial light to see anything meaningful, you had a solution, however imperfect. You could travel. Drive a few hours away from the nearest city, find somewhere genuinely remote, and the sky would, for a night at least, return to something close to what it once was everywhere. Dark sky tourism has become an entire industry built precisely on that principle, drawing people to remote deserts, mountain ranges, and national parks specifically because the sky there remains relatively unspoiled. That escape route depends entirely on satellites staying low enough and few enough that they remain largely invisible once the sun has fully set and the Earth's own shadow falls across their orbit. And for most of the current generation of satellites orbiting at relatively low altitudes, that assumption still mostly holds. Once you're standing in true deep night with the sun sufficiently far below the horizon, most current satellites pass into the Earth's shadow along with you and simply go dark, invisible until the next time their orbit carries them back into sunlight. But the newest generation of proposed orbital data centers isn't designed to operate at those lower, shadow-susceptible altitudes. They're being planned for considerably higher orbits, specifically because higher altitude means more consistent, less interrupted sunlight, which is exactly what a solar-powered computer running around the clock actually needs. At those higher altitudes, a satellite can remain illuminated by direct sunlight for the overwhelming majority of the night, long after the sun has set from your perspective on the ground, because it's simply high enough up that it hasn't yet passed into the Earth's shadow. Combine that persistent illumination with the sheer physical size of these proposed spacecraft, solar collecting surfaces spanning hundreds of square meters each, several times larger than the reflective area of a typical current-generation satellite. And you arrive at objects that aren't just numerous, they're individually bright. Bright enough, according to preliminary estimates based on their described dimensions and orbital altitude, to rank among the more prominent points of light in the entire sky, rivaling some of the brightest stars we can see, or in some configurations, potentially outshining every star entirely, trailing steadily across the sky throughout most of the night, every night, for as long as the constellation remains operational. There is no mention in the publicly available details of these proposals of any deliberate effort to reduce that brightness, no described coating, no sunshade, no orientation strategy specifically intended to minimize how much these satellites reflect back down toward the ground. The design priority, understandably from a purely engineering standpoint, has been solar collection efficiency and thermal management, not astronomical discretion. And it isn't only individual satellite brightness that researchers are worried about. There's a second, subtler effect that compounds the problem in a way that's much harder to escape by simply traveling somewhere remote. Even satellites too faint to be individually noticed by the naked eye still scatter a small amount of sunlight in every direction all the time, contributing to a general, diffuse brightening of the entire sky, a phenomenon researchers refer to as sky glow. At current satellite populations, this effect remains genuinely negligible, an amount of added brightness too small for the human eye to consciously register. But as proposed populations climb into the hundreds of thousands, and especially if additional proposed systems involving large orbital mirrors designed specifically to redirect sunlight down to specific locations on Earth on demand, are added into the mix, the projected increase in overall sky brightness becomes substantial enough to meaningfully degrade the contrast needed to see fainter stars, even in locations that have never previously suffered from any conventional ground-based light pollution at all. This is the part of the future that should genuinely unsettle you, more quietly than the collision risk, but in some ways more permanently. Collision cascades, catastrophic as they would be, are at least theoretically a solvable problem given enough time, enough caution, and enough international cooperation. But a night sky saturated with tens of thousands of moving reflective points of light, glowing faintly across its entire surface, isn't something that gets fixed by waiting 5 years for atmospheric drag to clean up an orbital shell. At the altitudes being proposed, with essentially no atmospheric drag to naturally remove anything, these satellites and their eventual successors would remain a persistent feature of the sky for as long as the constellation continues to be actively maintained and replaced, which, if the business model succeeds, means indefinitely. There would be, quite possibly, no remaining place on the surface of this planet where a person could stand, look upward on a clear night, and see the sky the way every single human being who ever lived before this generation was able to see it, simply by walking outside. That is not a hypothetical, distant, speculative outcome drawn from an extreme worst-case scenario buried deep in a research paper. It is, with startling directness, simply what the currently filed numbers describe if they are executed anywhere close to as proposed. The gap between where we stand tonight and the future isn't measured in some uncertain, distant span of decades. Based on the launch cadences described in the actual filings, dozens of these constellations reaching meaningful scale within the coming 10 to 15 years, it's measured in something closer to the span of a single generation, close enough that many of the people watching this tonight will likely live to see, quite directly, both versions of the sky. The one that exists right now, still recognizably ancient, still recognizably the same sky that guided every civilization in human history, and whatever comes after it. Which brings us, finally, to the question that everything in this story has actually been circling around from the very beginning. Not whether any of this is technically possible. We've established across everything we've covered so far that most of it genuinely is. The real question is whether any of it is something we should actually choose to do, given everything it would cost us. And whether, at this point, we still meaningfully retain the ability to choose otherwise at all. Part 9. What we actually know and what we're still guessing at. Before we go any further, I want to slow down and do something this particular story genuinely deserves. I want to separate what is solid, established science from what remains, at this point, informed but still uncertain projection. Because it would be easy, in a story like this one, to let the momentum of everything we've covered carry us straight into pure alarm, and that wouldn't actually be honest to the physics, or fair to the engineers currently working very hard on exactly these problems. Here is what is not in dispute: the physics of orbital mechanics, the speeds involved, the way debris propagates after a collision, the way heat can only escape a vacuum through radiation, the way radiation damages exposed silicon over time. None of this is speculative. It is measured, tested, repeatedly confirmed physics, the same equations that have guided every successful spacecraft mission since the beginning of the space age. When we say two satellites colliding at 11 kilometers a second will generate thousands of fragments, that isn't a guess. We have watched it happen in 2009, and we have the radar data to prove it. Here is what is also not in dispute. The current trajectory of satellite population growth is real, documented, and dramatic. 15 years ago, the number of active satellites in orbit could be counted in the low thousands. Today, it sits above 15,000, the overwhelming majority launched within just the past 5 years. That growth rate is not a projection. It has already happened, and the filings currently sitting with regulators describe an intention to continue that growth at an even steeper pace. What genuinely remains uncertain is scale and timeline, and whether the most extreme numbers described in these filings will actually be built as proposed, or whether economic, technical, or regulatory friction slows things down considerably before they reach anywhere near their full stated scope. This distinction matters enormously because history offers a useful, sobering lesson here. Ambitious space filings do not always become ambitious space realities. Companies have, across the history of the industry, proposed constellations that were later scaled back dramatically, delayed by years, or in some cases abandoned entirely once the actual economics of building and launching them became clear. A regulatory filing is a statement of intent and a claim on future spectrum and orbital slots. It is not a guarantee. Filing for 1 million satellites secures the option to build 1 million satellites without necessarily committing anyone to actually doing so. particularly if the underlying business case doesn't hold up once real costs are measured against real revenue. So there is a genuine, meaningful possibility that the full, most extreme version of this future never actually materializes. Perhaps the launch costs never fall as far as they need to. Perhaps the radiation damage to cutting-edge chips proves more severe in practice than current models suggest, forcing operators to either use older, less capable, more radiation-hardened processors, undermining the entire performance advantage the concept was built around, or to replace satellites even more frequently than currently projected, driving costs up rather than down. Perhaps regulatory bodies, facing mounting pressure from the astronomical community and from a public increasingly aware of what's at stake, eventually develop the legal authority and the political will to impose genuine limits, the kind current agencies currently lack. Any of these outcomes, individually, could meaningfully slow or cap the growth trajectory we've been describing throughout this story. And there are credible people within the aerospace and astronomy communities who believe some combination of these limiting factors will, in practice, prevent the very worst-case scenarios from ever actually unfolding at the full scale described in the most ambitious filings. But here is the part of this that I don't think you should let yourself off the hook on too easily. And it's the part that keeps serious orbital safety researchers awake at night even while acknowledging all of that uncertainty. You do not need the absolute worst-case, full-scale version of these proposals to come true in order for the risks we've discussed tonight to become genuinely serious. The modelling showing collision warning frequency climbing from once every several minutes to once every 22 seconds happened with roughly 15,000 satellites in orbit, a number we have already reached. The modelling showing the worst-case cascade timeline collapsing from 4 months down to under 3 days happened using that same current population, not some distant hypothetical future population. We are not describing risks that only become real if every single filed proposal gets built exactly as described. We are describing risks that are already measurably present today in the sky above you right now, and that will continue climbing steadily with every additional satellite added, long before anyone gets anywhere close to the full. Most extreme numbers sitting in the most ambitious filings. This is, I think, the honest and appropriately calibrated way to think about a story like this one. Not as a certain inevitable countdown to a specific catastrophic date, because that would be overstating what the evidence actually supports, but also not as a distant, comfortable hypothetical that can be safely set aside for future generations to worry about, because that would be understating a trend that is already measurably, actively unfolding right now in real time, faster than most people outside this specific field have any real awareness of. There's a useful way to think about risks like this one, borrowed from how safety engineers think about systems generally. It's not really about whether disaster is guaranteed to happen. It's about how much margin for error currently exists and how quickly that margin is shrinking. A bridge doesn't need to be certain to collapse tomorrow for engineers to be legitimately alarmed that its safety margin has fallen from comfortable to razor-thin over a short period of time. The alarm is warranted by the trend, not by certainty about the exact moment of failure. And by that standard, the trend here is genuinely alarming, even setting aside every uncertain, speculative extreme. The safety margin protecting Earth's orbital environment from a runaway cascade event has collapsed by a factor of roughly 40, from about 4 months down to under 3 days in the span of less than a decade, driven almost entirely by satellite population growth that has already happened, using technology that has already been built and launched, under regulatory oversight that has already proven by its own design, incapable of weighing that risk as a primary factor in its approval decisions. That is not a comforting story to tell you right before you fall asleep. I understand that. But it is, as best as the current evidence supports, an honest one. And I think there's something worth holding on to in the honesty itself. Because the alternative, either wildly overstating the certainty of catastrophe or quietly ignoring a trend simply because it hasn't reached its worst possible conclusion yet, would serve you far worse than simply understanding, clearly and calmly, exactly where things actually stand tonight. Which leaves us with the genuinely important question sitting underneath everything else in this story. If the trend is real and the margin is shrinking and the regulatory system currently in place isn't equipped to weigh the risk properly, what, if anything, is actually being done about it? Are there people working on solutions? Is there a version of this future where the benefits, global connectivity, distributed computing power, genuine scientific and economic progress, can coexist with a sky that hasn't been permanently sealed shut or permanently erased? That's where we're headed next, into the people and the ideas currently working to thread that exact needle, and what it would actually take to get there in time. Part 10. The people trying to thread the needle. It would be easy, after everything we've covered tonight, to assume that nobody with any real influence in this industry is taking the risk seriously. That isn't quite true, and it's worth spending some time with the people who are, because their work represents the actual, practical difference between the darkest version of this future and something considerably more survivable. Start with the tracking problem itself, because before you can avoid a collision, you first have to know, with genuine precision, exactly where everything is. For most of the space age, this task fell almost entirely to government-run military and civilian tracking networks. Ground-based radar and optical systems originally built during the Cold War to monitor missile launches and almost as an afterthought, repurposed to catalogue the growing population of satellites and debris sharing orbit with them. These systems are genuinely impressive, capable of tracking objects down to roughly the size of a softball across most of low Earth orbit. But a softball-sized threshold still leaves an enormous population of smaller, still lethal fragments completely untracked, invisible to the very systems responsible for warning satellites out of their way. In the past several years, a new generation of privately funded tracking companies has emerged specifically to close that gap, deploying their own dedicated radar and optical sensor networks, often achieving tracking precision considerably finer than the older government systems were ever designed for. Some of these companies have partnered directly with major satellite operators, feeding higher resolution tracking data directly into the automated avoidance systems we discussed earlier, meaningfully improving the accuracy of collision predictions and reducing the number of unnecessary evasive maneuvers, which matters more than it might initially sound like, because every unnecessary maneuver burns limited onboard fuel, and fuel, once exhausted, is what eventually turns a controllable, dodging satellite into an uncontrollable piece of debris in its own right. Then there's the harder, more ambitious end of this work: active debris removal. For decades, this remained largely theoretical, an obvious idea on paper, physically and financially daunting in practice. Sending a spacecraft up specifically to rendezvous with an uncontrolled, tumbling piece of debris, matching its unpredictable rotation, safely capturing it without triggering the exact kind of collision you're trying to prevent, and then either guiding it down into a controlled re-entry or moving it to a genuinely inert graveyard orbit, is an extraordinarily difficult engineering problem, several steps harder than a standard satellite mission. Despite that difficulty, Several missions have now successfully demonstrated pieces of this capability in real orbital conditions. Spacecraft have successfully used robotic arms, magnetic capture systems, and even large deployable nets to rendezvous with and secure defunct satellites and spent rocket stages, guiding them towards safe, controlled disposal. These missions remain, for now, expensive, one at a time demonstrations rather than a scalable, routine industrial process. But they represent genuine proof that the core technical challenge, actively removing dangerous debris rather than simply avoiding it, is solvable given sufficient investment and sufficient institutional will to prioritize it. The genuine, difficult, unresolved question is economic rather than technical. Who pays for it? A company that puts a satellite into orbit generally has no legal obligation and often no direct financial incentive to pay for the eventual removal of debris that satellite might one day become, particularly decades after it stops operating, potentially long after the original company itself no longer exists in its current form. Some newer international guidelines have begun requiring operators to demonstrate a credible plan for deorbiting satellites at the end of their operational life, generally within a set number of years after a mission concludes, and to set aside a portion of the spacecraft's fuel specifically to accomplish that controlled deorbit. These requirements represent real, meaningful progress, but they remain, again, guidelines rather than universally binding international law applied unevenly across different countries and different regulatory frameworks, with genuinely limited enforcement mechanisms behind them. There's also meaningful work happening on the astronomical side of this story among researchers who aren't trying to stop satellite constellations from being built at all. Recognizing realistically that the connectivity and computing benefits they provide are enormously valuable and effectively impossible to simply prohibit, but who are instead working directly with satellite operators to reduce the specific harm these constellations cause to ground-based astronomy and to the naked-eye night sky. This collaboration has already produced some genuinely useful results. Engineers have experimented with specialized dark coatings and deployable sunshades specifically designed to reduce how much sunlight a satellite reflects back down toward the ground, and some operators have adjusted the orientation of newer satellites during the specific portions of their orbit when they're most visible from the ground, measurably reducing their apparent brightness during exactly the hours when human eyes and astronomical telescopes are most likely to be watching. These are incremental improvements, not complete solutions. A dimmer satellite is still a satellite, still an artificial point of light crossing a sky that once had none. But dimmer is measurably, meaningfully better than the alternative, and it demonstrates that satellite operators, when directly engaged by the scientific community and genuinely willing to listen, are capable of incorporating these concerns into their engineering process without necessarily abandoning their underlying business goals. The honest, complete picture, then, looks something like this. The technical tools required to meaningfully reduce both the collision risk and the visual impact we've spent this entire story describing largely already exist or are actively, rapidly being refined by genuinely capable, well-resourced teams of engineers and researchers. Better tracking. Real, demonstrated debris removal capability. Dimming technology that measurably works. None of this is speculative, futuristic technology sitting decades away. Much of it is already flying, already being tested, already producing real, measurable improvements. What remains genuinely, critically unresolved is not whether these solutions can work. It's whether they'll actually be adopted consistently, universally, by every operator sharing this crowded, finite orbital environment, quickly enough to meaningfully outpace the sheer rate at which new satellites are currently being proposed and launched. A single company voluntarily dimming its satellites and carefully managing its own debris helps, genuinely, meaningfully, but it doesn't fully solve a shared common-style problem if a dozen other companies and countries, filing their own competing constellations into the exact same crowded orbital shells, don't feel any comparable pressure or obligation to do the same. This is, ultimately, less a technology problem at this point than it is a coordination problem. And coordination problems, historically, tend to get solved only when the cost of continued inaction becomes undeniable enough, and widely enough understood to force genuinely binding agreement between parties who would otherwise each individually prefer to keep moving as fast as possible, unconstrained, for as long as they can get away with it. Which brings us finally close to where this story has to land. Because everything we've covered tonight, the physics, the economics, the regulatory gaps, the emerging solutions, all of it eventually funnels down to a single, unavoidable question that isn't really a scientific question at all anymore. It's a question about what kind of relationship we actually want to have with the sky above us, and whether we're willing to accept the discomfort of slowing down right now while we still genuinely have the choice. Or whether we'll simply keep moving at the current pace and find out, empirically, exactly how much margin for error we actually had left. That's where we're headed, into the closing part of this story. Part 11. The choice hiding inside the momentum. There's a particular kind of trap that technological progress falls into again and again throughout history, and I think it's worth naming plainly before we get to the end of this story, because I believe it's exactly the trap we're standing inside of right now. The trap works like this. A genuinely useful, genuinely valuable technology emerges, solving real problems for real people. Early adoption happens quickly, driven by legitimate demand, and because the technology is new, the regulatory and legal frameworks meant to govern it lag meaningfully behind, simply because nobody could have written rules for a problem that didn't exist yet. In that gap, the technology keeps expanding, faster than anyone is tracking, faster than the institutions responsible for oversight can meaningfully respond to, because every individual step forward seems small, reasonable, and defensible in isolation, even as the cumulative trajectory quietly carries everyone toward a destination nobody specifically chose or voted for. This is, more or less, exactly the pattern we've traced across every part of this story tonight. Nobody sat down at any point and deliberately decided, as a considered weighed choice, that the night sky should belong primarily to machines within a single generation. Nobody voted on whether the risk of a runaway orbital collision cascade was an acceptable price to pay for faster AI computation. These outcomes, if they happen, will not have been chosen. They will have simply accumulated, filing by filing, launch by launch, each individual decision defensible enough on its own narrow terms, adding up, in aggregate, to a future that almost nobody, if asked directly and given the full picture, would have actually selected. And I think that distinction between an outcome that gets chosen deliberately and an outcome that simply accumulates by default is the single most important thing to understand about where we actually stand tonight. Because it means the story isn't over. It means the future we've spent this entire evening walking through in careful, sobering detail isn't a fixed, locked-in certainty. It is, right now, still genuinely a matter of accumulating decisions, decisions still being made, decisions that could still, in principle, be made differently. Consider what that would actually require, concretely, rather than as vague, comfortable, feel-good sentiment. It would require the specific regulatory gap we spent an entire part of this story examining. The fact that an agency built to prevent radio interference is currently the primary body reviewing proposals with this scale of consequence to actually be closed. Not through some distant, idealized global treaty that may never materialize, but through the far more achievable, far more immediate step of expanding the legal mandate of existing agencies, or creating new ones. Specifically empowered to weigh collision risk and night sky preservation as genuine binding factors in the approval process, alongside radio spectrum interference, rather than as an afterthought with no real regulatory teeth behind it. It would require the debris mitigation guidelines that currently exist only as voluntary recommendations to become binding, universally enforced requirements. Genuinely applied across every operator, in every country, launching into these shared finite orbital shells, closing the loophole that currently allows companies to simply choose the regulatory jurisdiction with the lightest, most permissive oversight. It would require satellite operators to treat brightness reduction and debris mitigation not as optional. Goodwill gestures offered occasionally in response to outside pressure, but as fundamental, non-negotiable engineering requirements built into every satellite design from the earliest planning stages, the same way structural safety margins and radiation tolerance are already treated as absolutely non-negotiable throughout the aerospace industry. None of this is technically impossible, genuinely none of it. Every piece of it lies well within our current technical and institutional capability. Right now, today, what it actually requires is something considerably harder than any individual engineering problem we've discussed tonight. It requires the will, collectively, across companies and countries that don't always share the same immediate incentives to slow down, even briefly, even partially, at the exact moment when every individual competitive pressure is pushing everyone involved to move faster instead. That is, I recognize, an enormously difficult thing to actually ask for, and an even harder thing to realistically expect. Companies racing each other for market position rarely slow down voluntarily, purely out of long-term caution, when their most immediate competitors show no obvious signs of doing the same. Nations racing each other for strategic and economic advantage in space rarely wait patiently for comprehensive, binding international agreement before proceeding with their own individual plans. This is, in the most fundamental sense, the exact same underlying structure as every other genuine tragedy of the commons humanity has ever faced. Individually rational decisions made by individually reasonable actors, each one following their own immediate incentives, adding up, in aggregate, to a collectively catastrophic outcome that nobody involved specifically wanted or intended. But here is the one thing that genuinely, meaningfully distinguishes this particular commons problem from most of the others we've faced throughout history, and I think it's worth sitting with, quietly, before we close this story out for the night. Most environmental and resource crises unfold slowly enough and diffusely enough that the connection between individual daily choices and eventual large-scale consequence becomes genuinely difficult for any single person to feel or perceive directly in any immediate, visceral way. This one is different. This one, unusually, is something you can walk outside and see with your own eyes, right now, tonight, if the sky above you happens to be clear. Go outside. Look up. Count how many points of light you can actually identify moving steadily, deliberately across the sky, rather than remaining fixed in the traditional, ancient patterns of the constellations. A decade ago, on most clear nights, in most locations, that number was close to zero, an occasional single satellite drifting past if you happened to be watching closely at exactly the right moment. Tonight, in many locations, especially shortly after sunset or shortly before sunrise, when satellites remain sunlit while the ground below has already fallen into full darkness, that number is measurably, noticeably higher, and it is still climbing. That direct, personal, visible connection between an abstract, distant regulatory filing and something you can actually observe with your own unaided eyes is genuinely rare in the broader landscape of large-scale technological risk. Most existential scale risks remain comfortably invisible, abstract, easy to intellectually acknowledge while still emotionally, practically ignoring in day-to-day life. This one, at least the visible sky portion of it, is not like that. It's sitting directly overhead, accumulating in a way that's genuinely directly observable incrementally, night by night, for anyone willing to actually step outside and pay attention. I don't think that visibility, on its own, is going to be sufficient to change the underlying trajectory. Awareness alone rarely, by itself, shifts deeply entrenched economic and competitive incentives at the scale we're discussing tonight. But it does mean this particular story isn't quite as distant, or as abstract, or as easy to set aside for someone else, some other generation, to eventually deal with, as most conversations about existential scale risk tend to feel. This one is, quite literally, visible from your own backyard, tonight, if you simply choose to step outside and look. Part 12. What's left when you turn off the light? There is an old, simple fact about looking up at the night sky that most of us stopped consciously noticing a long time ago, precisely because it was always so effortlessly available. Every single human being who has ever lived until this exact generation has looked up at the same essential sky. The constellations shifted only imperceptibly across entire lifetimes. The stars that guided ancient sailors across open ocean were, give or take a few thousand years of barely perceptible drift, the same stars that guided every civilization before them, and the same stars your own grandparents once pointed out to you as a child. That continuity, stretching back across the entire span of human history, is not something we tend to think of as a fragile, finite resource. It has simply always been there, quietly, patiently, every single clear night, asking nothing of us in return except that we occasionally remember to look up. What we've walked through together tonight is the story of exactly how that continuity, for the first time in the entire history of our species, has become something that is not simply a given anymore, something that could, within the span of a single generation, genuinely change, permanently, not because of some slow, natural, cosmic process unfolding across millions of years, but because of a specific, traceable, ongoing sequence of decisions being made right now, largely without most of the people who will actually inherit the consequences having any real say in the matter. We've followed the thread from a hungry, overheating data center outside a single American city, drawing more electricity than entire neighborhoods just to answer typed questions, through the genuine, elegant physics of why space, despite feeling impossibly cold, is actually a remarkably difficult place to cool anything down. Through the quiet, invisible violence of radiation slowly degrading the most advanced silicon we've ever built. Through the razor-thin, rapidly shrinking safety margin currently protecting every single spacecraft in orbit from a collision cascade with potentially permanent, planet-sealing consequences. And finally through a regulatory system built decades before any of this was even conceivable, straining now to somehow govern a problem it was never actually designed to address. None of what we've discussed tonight is certain in the sense of being an inevitable, locked-in, unavoidable future. I want to be genuinely honest with you about that one more time before we close, because I think false certainty in either direction would be a disservice to a story that actually deserves careful, measured, honest attention rather than either panic or false comfort. The most extreme version of this future, 1,000,000 active satellites, a sky more crowded with machines than stars, a collision cascade sealing off orbital access for generations, remains, genuinely, a possibility rather than a certainty. Economics may intervene. Engineering challenges may prove harder in practice than current models suggest. Regulatory frameworks may yet evolve quickly enough to meaningfully slow the pace before the very worst outcomes have any real chance to unfold. But the underlying trend, the steadily accumulating population of objects sharing an increasingly crowded, finite orbital environment, the steadily shrinking margin for error, the regulatory gap that has so far shown little real sign of closing on its own, all of that is not speculation. It is already quietly, measurably underway in the sky above you right now, tonight, whether or not you happen to notice it before this evening. Perhaps the most honest way to think about tonight's story is this. We stand right now at one of those genuinely rare moments where a civilization can still meaningfully choose the shape of a future that hasn't fully solidified yet, rather than simply discovering, after the fact, what the future turned out to be. That kind of moment doesn't come along often, and it doesn't tend to last very long once it arrives. Because momentum, once it builds sufficiently, has a way of quietly closing off the very choices that once felt entirely open. Whether that moment gets used wisely, whether the coordination and restraint required to preserve both a genuinely useful orbital future and a genuinely visible night sky actually materializes in time, isn't a question physics can answer for us. But physics only tells us what happens if current trends simply continue unaltered. It cannot tell us whether they will. That part, entirely, remains up to the decisions still being made, filing by filing, launch by launch, across the exact years you happen to be alive to witness them. So tonight, before you drift off, I'd ask you to hold on to something small and simple and entirely within your own reach. The next time the sky above you happens to be clear, step outside for a moment and just look up. Not searching for anything in particular, not counting satellites or worrying about filings or running through any of the numbers we've walked through together tonight. Just looking the way people have always looked at a sky that has, for the entire span of human history, simply been there, quietly, patiently, waiting, because that sky, in its current, still mostly undisturbed form, is not a permanent, guaranteed feature of the world you happen to live in. It is, right now, tonight, still something we get to choose to keep. And somewhere between the quiet hum of a data center pulling electricity out of an overloaded grid, and the silent, patient light of a star that began its journey toward your eyes long before you were born, that choice is still, for now, sitting gently in our hands. And maybe that's the quiet thought worth carrying with you into sleep tonight. Not fear of what might happen, but a kind of tender attentiveness to what we still have, while we still have it. The stars above you right now have been burning since long before the first human ever looked up and wondered what they were. They will keep burning long after every satellite, every data center. Every filing and proposal we talked about tonight has come and gone. What's actually fragile isn't the sky itself, it's our relationship to it, our willingness to keep it visible, keep it dark, keep it ours in the way it has always belonged to everyone who ever paused to notice it. If tonight's journey helped you see that a little more clearly, consider subscribing, so future nights like this one can find you again and share this with someone who still remembers what it felt like to find the Milky Way. Rest easy, the sky is still watching over you.